Okay, so here in this model, we are going to talk about a filter. Okay, so in this model, we continue with the filters. Again, this is a first order filter. And here we understand how this circuit works. So here we have a capacitor and here we have a resistor. This is as opposed to the previous model where we have a resistor and the capacitor. And in the previous model, we've seen that this circuit works as a low pass filter. Right. And now let us see how this circuit works. So we have a capacitance and we have a resistance here. What we have is this input voltage Vi of t, and we develop output voltage across this resistance called as Vo of t, obviously, and there is a current flowing through this network is defined as I of t. So what we see here, we can write the apply KVL, that is Kirchhoff voltage law, to obtain the frequency response. We will obtain the frequency response of this network. So what we do here is we apply this KVL, Vi of t, that equals I of t into 1 over j omega c. That is the impedance of this capacitor multiplied by the current. So right, I into R or I into impedance. For the capacitance, we have this kind of relation plus I of t into R. So that would be I of t in bracket 1 over j omega c plus R. So that's what the equation 1 says. Similarly, the output voltage is given as, which is the voltage across this resistor over here, is simply the current flowing through the resistor multiplied by its value. Okay, and with this we have I of t will be the voltage divided by this resistance. So let us have this equation number 2, and we plug back the value of I of t right in this equation. So Vi of t takes the form as Vo of t divided by R, which is the value of I of t, in bracket 1 over j omega c plus R. All right. So we know that this is the expression we can have, and from this we can try to obtain the expression for the gain. So what we do here is we write the expression to obtain the gain, which is Vo of t, Vi of t, and this would be calculated as R divided by 1 by j omega c plus R. So as we can see here, we take the Vo by Vi. So R divided by this factor. Okay. And if we want to simplify this, so we can always write, we multiply, we divide the numerator and the denominator by 1 by R, so it becomes 1 plus 1 by j omega RC. Okay, that's how we get the expression. And how to obtain the expression for the magnitude would be 1 over square root of 1 square plus 1 by omega RC whole square. That's the magnitude. So can we write it like this? Will be 1 plus RC is 1 over omega c, so it would be omega c by omega whole square, right? And similarly, the angle would be Vo of t, Vi of t, it would be tan inverse 1 by j omega RC by pi 1. So it would be j is 90. So tan inverse omega c by omega. This is how it will go. So let us understand the first case where we now assume that omega is 0 and omega is very, very less than omega c. So in that case, if we look at this transfer function right over here, so this takes the form omega is very, very less than, so it is 0 basically. So this term is infinite and 1 over infinity is 0. So this term becomes 0 at omega equal to 0, and as omega starts to increase, but it is still very, very less than omega c, this term goes decreasing, right? From infinity it starts decreasing. So this denominator goes on increasing, and therefore the denominator starts decreasing, and therefore the gain starts increasing, right? Yes. Wait. So we have this omega starts to increase. For instance, it is still very, very less than omega c, but it starts increasing, then this goes down, and then denominator goes down. So approaches 1. Yeah, so then this magnitude starts approaching 1. So how we understand this through the plot? Let's say we have this plot over here, and this value at omega is equal to 0. What? So we have this magnitude, which is gain a, and a is nothing but this value over here, and this starts approaching till the value of omega. So it starts approaching 1. So we'll write like this. Okay, as omega is increasing until it reaches the value of omega t, omega c here. Okay, and the magnitude is 0 right over here. So we'll write that at 0 it is 0, and for this case it starts approaching unity, right? And what about the angle? Angle would be calculated as tan inverse of omega c by omega. So omega is 0 is basically it's tan inverse 0 is 0. Tan inverse infinity actually. So it is yeah. So tan inverse 1 is 45 actually. It reaches 45 or what? Wait, we will just see that. It is 0 actually. It is 90. No. So phase omega c by omega, so tan inverse 0, and omega is very less than omega c. Omega c dominates actually. So 10 times or 100. 89 or something, right? So when for this case, it's very less than, let's say there is a, it's a fact by a factor 100. So it has a value of 90 degree. Approximately 90 degree. And then omega starts to rise, then this value starts dropping from 90. So for the phase, we see here, you can always draw this. So this is your phase, and we start somewhere from 90 degree, okay, and it starts dropping till omega c. At omega equal to omega c, we have to see what value it takes, because then it tan inverse 1 for omega equal to omega c, and tan inverse 1 is a 45. So it touches this angle right over here. So this is 45 degree, and finally it will go to 0. We'll see that. Okay. So for the case 2, omega equal to omega c, we see that magnitude takes the form of 1. So we come back to expression omega equal to omega c. So magnitude is 1 by root 2. It's 1 by root 2, which is 0.707, and the angle is VO VI over T VO of T, and that's basically tan inverse 1, so it is 45 degree. Okay. We'll write here tan inverse 1, so that is 45 degree. And how to plot these two? So we see that we have this value over here. This is, we'll say that this is 0.707. So it is minus 3 dB point. Okay, in decibel. In the previous model, we've seen that. And this is that phase would be 45. And third case would be case 3, where omega is very greater than omega c. So we see that in that case, magnitude reaches what value? So here, right over here, omega is exceedingly greater than omega c, let's say by a factor of 100. So this goes to 0, right? This denominator goes to, this factor goes to 0. So the gain will be 1. Okay, so we'll say it's approximate, obviously, approximately 1. So we draw that right over here, and it will stay 1. For this case, omega is very greater than omega c. Okay, and this is approaching infinity. This is also omega, right? This is omega equal to 0. This is the same axis. This is omega equal to omega c. This is omega tends to infinity. Okay, and when omega tends to infinity, for the phase, we say that tan inverse right over, this is infinity, so tan inverse is 0. Tan inverse 0 is 0 actually. So we come back here and we write that the angle of tan inverse 0, that is 0 degree. Fine. So to mark that, here we see this is 0 degree. So this is how this filter looks like. So we see that this is the stop band, actually. Stop band, because we see the gain is attenuated. This is pass band, because we see that there is a constant gain for this frequency over, and this is cutoff or break frequencies. All right. And this is how we can explain the working of filter, and this is called as high pass filter. All right. So because it is passing the frequencies above omega c, which is the cutoff frequency, that's why it's called as first order high pass filter. So that's all for this module, and we'll continue with this further explanation.